Okay. Well, thank you very much. Thank you for the organizers to giving me the opportunity of being here today, speaking to all of you, and speaking a bit about something that is a bit different than what we've heard about, which is about the measurement of atomic data that many of you will be using for your work in white dwarfs. So I want to give you a bit of an overview of what we do in the labs, what is the situation in terms of atomic data, what is done, what needs to be done, and also that you have an idea of what a lab looks like, what kind of things we do in a lab. And finally, I think the aim of this talk is really to foster collaborations between you guys and people working in laboratories. So a bit the overview of my talk. I will speak very briefly about who we are so that you can put us a face. And then why is this important? Why is measuring atomic data very important? And what is the current situation? Then I'll speak a bit about what we measure and how we measure it in the lab. And finally, a few words about what we can do for you to help you. So we start about who we are. So I come from the Atomic Spectroscopy Laboratory at the University of Valladolid. Valladolid is a city, you can see, in the central part of Spain. It has a really old university from the 13th century, so it's one of the oldest of Spain. And our group was founded, the lab was founded 45 years ago by Professor Santiago Mar. And it was mainly interested in measuring atomic parameters, especially Stark broadening, Stark shifts, and transition probabilities. What happened with the lab is what is happening with many other labs around the world, sadly. That is that when the PI retires, the group is forced to close because there's nobody to continue with the group. And this is what happened to our group. It closed 4 years ago when Professor Mar retired. And then I reopened it a year and a half ago with a fellowship from the Spanish government. So the idea of reopening the group is not only to continue doing what we were doing, but also adapting the lab to measure some of the most needed data in astronomy in particular. So at this moment, we are a small but hopefully growing group. We are 2 people, myself and a PhD student, Protus, who joined us from India after passing through France. And he joined half a year ago. And as it happens on many labs, we rely on retired people a lot. And this happens in our lab, it happens a lot in NIST. So we still have the help of Professor Mar. We don't work alone, we have a network of collaborations. The main one is the group of Professor Juliet Pickering at Imperial College, because it's where I spent a few years doing my postdoc. We also collaborate with a group of Dr. Henrik Hartmann at the University of Lund. Lund, one of the oldest universities in the study of atomic spectroscopy. And we work also with Gillian Naif at the National Institute of Standards and Technology. So why is this important? Why does it make sense that I'm here speaking to you today? Well, an example of this paper that we listened to Paula's talk this morning, this is from her paper. And this is basically, if you measure a spectra, if you do a spectroscopy from a white dwarf atmosphere, this is what you get. And what do you do with this? Well, you want to identify elements and you want to know how much of those elements you have. And to do this, you need wavelengths, you need line positions, and you need some parameter that tells you something about the intensity of the line. And this parameter is transition probability. So just a brief note about transition probabilities here so that we know what we are speaking about. So transition probability is what we also call the Einstein coefficient for spontaneous emission. So you have 2 energy levels and the electron is in the upper energy level for how long it's going to be there. That's what it's telling me. And the transition probability is a parameter that is defined for emission. For astronomers, you tend to work with the F, with oscillator strength, which is a parameter which was defined for absorption. So we have a way of passing from one to the other one, which is this equation. But something we need to be careful about is that, as you can see, the transition probability is always accompanied by this G, which is the statistical weight of the upper energy level. because the transition probability was defined for emission, and F, the oscillator strength, is always accompanied by this G of with the lower energy level. So be very careful, because normally when we say astronomers want log GF and we don't specify what G that is, if it's the upper energy level or the lower energy level. So if you want to pass from transition probabilities from some author to get your log GFs, you need to take this into account. And this again from Paula's paper. As someone working in atomic spectroscopy, what I'm interested in these papers is tables like this, in which you are telling what lines you are using from different elements. Something to take into account if you want to do studies of chemical abundance, you'll use at some point, or you'll be created a synthetic spectra with which you'll fit your measurements. But at some point, what you want is chemical abundance, and you'll have some expression where you have your oscillator strength and the wavelength. So what you need to take into account is that the uncertainty in these parameters, in wavelength and in oscillator strength, is going to have a reflection in the uncertainty of your abundance. So if you look at this table, for example, for neutral aluminium, only one spectral line was used, which means that the uncertainty in the abundance is going to come from this oscillator strength, only one oscillator strength. So this is a case in which it's extremely important to have good atomic data for your line. Other cases, for example, we have for titanium, you are using many different spectral lines. So even if some of those data is not too good, maybe you can compensate with the other lines. Okay. So if you have to look for this data, where can you go? Okay, one of the classical places to go is the database of NIST. So things to consider about this database is that what is included here is critically review compilations of data. This means that we authors produce data, and this data doesn't go directly into the NIST database. A compilation process needs to happen. Okay, at this moment, there's only one person doing compilation processes at NIST, and it takes a long time. This means that there are long delays between the time when we publish our data and when this data actually appears in the NIST database. Something very important also is that they provide uncertainties, which is something we don't find in other databases. So if we go to this database and click there in lines, we could look for information about this information for this neutral aluminium line, which appeared in the table before. And you see that they gave us different pieces of information. Very importantly, that B+, that is the accuracy that NIST assigns to that line, with A being the highest, the best quality, and then D, E, that would be very low quality. So we see there a B. Okay, that's good. Okay, that's not bad. The other important information they give us here is these transition probability references. So they are telling you where this data was taken from. And in this case, they give us these two references. So you can see the year of these references, 1999, basically. Okay, so this is like 20 years old. But NIST also give us not only data, but a bibliography section where they upload all the papers that have been published, even if the data doesn't appear on the database. So this for you might be interesting, because you could go and look at the latest publications for certain elements of your interest. So if you click there when they say up there, the bibliography, what we would find is this, and this is updated. So you can see we have papers from 2019. These two papers are theoretical calculations, but this hasn't been included in the database because it hasn't been reviewed. Okay. You have other databases. You have also VALD, I'm sure like some of you would use. You have Kurutz. Something important to consider about Kurutz database is that it includes semi-empirical calculations. So it's theoretical data. And NIST normally, when possible, is experimental data. But Kurutz is semi-empirical, which this means is that if for some element we have some experimental data, Kurutz includes that in his calculations. So the results that he gets are better, are closer to reality. So it also depends. The accuracy of Kurut's database depends on the fact, is there any experimental data for certain elements? So this is something to take into account. But of course, Kurut's has only data up to Z equals 30. So if we want heavier elements, we can't go there. We do these studies about atoms. How long does it take the analysis of one ion? Okay, this is the Grothian diagram for singly ionized iron. It's all the possible transitions that I can get in iron. Give this to a PhD student, and this is going to take a PhD plus a few years of postdoc. And it will give him, if he's lucky, 2 or 3 publications to publish this. The data then everyone is going to use. Okay. So this is the problem with this kind of studies, that they take a very long time. And you don't get many papers out of them, basically. How many people? Because if it's projects that take a long time, but there are lots of people working, this is not a problem. But what is the current situation in our field? Okay, so here I have some of the main groups working. And you can see, if you see the number of people working in each group, that they tend to be really small groups. And not only that, in some of these groups, like for example, in NIST, one of the members, and there's one member basically in charge of a lab that has like 7 different instruments, and it will be retiring soon. So I think people have this idea that NIST is a massive place full of people creating all the data you need. That's not the case. So this is something to consider. So we are very small groups and struggling somehow to continue. Is there work that needs to be done? Yes. So this is what NIST tells us, for example, for neodymium-3. Now neodymium very popular for neutron star mergers or the rare earths. Basically, there's nothing done. So incredible quantities of work is still to do. So what do we measure in the lab? And how do we measure it? But something to consider is that when you are looking at the spectra of white dwarfs, for example, atmospheres, you are looking at absorption spectra. But what we do in the lab is emission spectroscopy. So we need to create this light, and for this we use a lamp, as you see here. So to obtain this spectra, that is what we are going to use to measure our data, we need 2 things. We need a light source, and once we have produced the light, because you have the light coming from your white dwarf or from your star, but we don't have it, we need to produce it. Once we have it, we need to separate it into its different wavelengths so that we can get a spectra. So we need 2 things. We need lamps and we need a spectrometer. So let's have a quick view about the different kinds of lamps and instruments that we have. So your light source, imagine you need data to analyze the spectra of a white dwarf. The first thing you should tell to the person who's going to measure the data is what kind of data do you need? What ionization stage? Do you need neutral magnesium, singly ionized, doubly ionized? That's the element. So considering this, we would choose one lamp or another one. So you can see different kind of lamps give us different ions. Here, what I've put is a list of the most common used lamps, and in what labs you can find it. Not all the elements work in all the lamps. So this is a lot of our time is spent trying to figure out how to make an element work in a lamp. So that you have an idea of what a lamp looks like. This is a selection of lamps. So for example, in our laboratory in Spain, we have a pulse discharge lamp that is used to measure noble gases, mainly, and hydrogen, helium. And we have now a hollow cathode lamp that is used for metals. But you can get other kind of lamps, like a Penning discharge, which also has magnets. So you can get higher ionization degrees in this lamp. So this is about the light sources. What about the instruments? What kind of laboratories do we have? So here you have an example. This is our laboratory in Spain. And what you can see, well, I just pointed. There you can see just above my finger, that is the spectrometer. It's a diffraction grating spectrometer. And there you have all the parts for like introduce the gas that you want to put in your lamp, and then all the optics. Other kind of labs. Here you have the laboratory at Imperial College. What they have is what is called a Fourier transform spectrometer, which is basically a Michelson interferometer we measure an interferogram, and then we do a Fourier transform. So it's a completely different technique. And there you have the main instrument. Completely different kind of instrument. This is a massive, this is a 12-meter spectrometer at NIST that we use to measure if we want to go very low into the UV. So you can measure down to 50 nanometers. And you can see it has that size because of the spectral range we want to measure and the resolving power that we want to get. So what instrument do we need to use? If you come to us, measure some data, and we need to choose an instrument, but basically we need to choose the appropriate one. So you need to tell us what is the resolving power you need. It depends on the data you are using, the resolving power of the instrument with which you collected your data. And also in what spectral range you need your data. Okay, so you see, if you want to go very low into the UV, we could only use this instrument. And you see, we have in 10 to the 5 resolving power. Whereas if we go to the Fourier transform spectrometer, it's an order of magnitude higher. But if you compare these resolving powers to the resolving powers of different galactic surveys, you see that in general, they are much higher than the ones. So sometimes I have this feeling like, is it necessary to have this such high resolving powers? In principle, yes, because we should measure data with much higher accuracy that you see the data then, so that you can fit your lines well. Some interesting things, if you want to look at weak lines, sometimes having super high resolving power is not the best thing. So this is the same spectrum measured with grating instrument and with a Fourier transform. You can see the lines are much more resolved in the Fourier transform, but something that we can see is that weak lines that are very weak in the Fourier transform spectrometer, they are much more intense in grating. And this is because of the way the Fourier transform spectrometer works. So if you want to look at weak lines, it might be better to use an instrument with a grating. We can also measure things like this, the hyperfine structure. We can also measure isotope structure of lines. If we don't have enough resolving power with a Fourier transform spectrometer, we could use another instrument, which is a Fabry-Perot, which has a resolving power up to 10 to the 9. So here we are adding lots of orders of magnitude. And this is an instrument that we are installing now in our laboratory also. So here you can see basically it would be a Fabry-Perot, but it's not operating as an ETA alone. It's a spectrometer, so one of the mirrors would be moving. Once we have all these, what do we get? We get a spectral line, we feed this to a mathematical function, and we get the center of the line from where we get the wavelength, we get the full width at half maximum, and then the area under the profile. And this area under the profile is what we use to obtain transition probabilities. Why? Because the intensity of the line is going to be directly proportional to how probable that transition is and how many atoms I have emitting. So this is what we use to obtain experimental transition probabilities. We need to measure intensities of lines. We take into account all the sources of uncertainty in our measurements. So calibration, signal to noise ratio, do I have a blend? So we are really careful and very obsessed with uncertainties when we measure our data. So you can trust basically the uncertainties we assign. You know that NIST, for example, gives you the uncertainty with these letters. And what I would say is, please, we put a lot of effort in measuring these uncertainties. Sometimes it takes longer than measuring the data itself. So use them. Use them then for your studies of chemical abundance. Finally, we would give our results in a table like that. We measure transition probabilities, but because we know normally you want the log GFs, we'll also give you the log GFs directly. But if you found some paper where the log GFs were not given, you could obtain them yourself. And basically, this is what we do, but how can we help you? Well, in different ways. We can help you with a critical evaluation of atomic data. So let's say that you have to analyze a spectrum, and there's lots of data in the bibliography. Maybe there's not the data for the lines you want and the NIST, but there are new publications, and you don't have the expertise to choose which one is better. So we can do that work for you because we are more familiar with how to obtain data and how it's been measured. Then you could decide that there's not the necessary data for you to analyze your spectra, in which case we could measure new or improved data. And we could also use, this is sometimes happens when if you use different data, you get different results. We could try and dig out to see what the problem might be with the data. To give you an idea, this is from this paper from Gillian Neff at NIST. And it was basically speaking a bit about the situation of our field. Here what you can see is the number of papers, experimental translation probabilities over the years. And you can see how it declines. So this is a worrying situation, and that's what we are trying. We want to collaborate with you and not only work together in projects, but work together in applying for funding, because we need to keep our laboratories running. So we can't really give a PhD student, here you have to do the entire atom of iron. That is not very efficient. Where it's much more efficient is like, you tell us, I need these few lines, and we focus on them. And I think that would be a better way to go forward. That would be more realistic also for our labs. We could keep them going. And that's all. As I would say, if you want to come and speak to us, if you need new data, if you have ideas that we could apply for funding together, we are open for any requests that you have. Thank you.
Very nice talk. Question for Teruca? Maybe I'll start with one. I'm just curious, what are your criteria when you go through different references? Let's say different publication report the same transition. Could you kind of briefly walk us through what are your criteria of assessing this one's good, this one's better?
Okay, that's a good question. So the good, basically, if we want to do a perfect evaluation of data as they do at NIST, what you have to take is you take different data from different authors and try to put it in a common scale. And when put it in a common scale, you may realize that some data disagree with the other data. But when putting data in a common scale, you are making lots of assumptions also. So it's not a perfect method. Then I would say that sometimes you know that some experimental method is more accurate than others. Or if you have data measured 30 years ago and you have data measured now with a Fourier transform spectrometer, we know that the accuracy is much higher in this case. So, but sometimes maybe we don't know. And all what we can say is like, provide you the data, say we have these. This set of data might have these problems, this set of data, and you can try and see what would work better.
I'm sure we use this a lot in all our research.
Yeah, thanks. Simon Bloin, University of Victoria. Very great, interesting talk. So we often use VALD for the line list for polluted white dwarfs. Can you say something about VALD? How much should we trust it compared to NIST or the Kourous line list, for example?
Yes, in fact, I don't know if I completely removed it. I had a slide about VALD, and because I thought it was going to be too much, I didn't include it. So VALD, if you go to their website, what they say is that they compile data for different authors. First of all, it's very focused on astronomy. And what they do sometimes, they take data from different authors and try it, for example, to produce synthetic spectra and check the synthetic spectra they get with observed spectra of some star. And doing this process, they basically come to the conclusion that some data is better than others. So on many occasions, we are getting emails from people about, oh, this data doesn't seem to work, or, so there's collaboration with people involved. But what they say in their website also is like, they are ranking their data, they're ranking the data they put in VALD following what they think is a good criterion, but it says the user might choose a different ranking. So I think this gives you an idea that, again, I'm not an astronomer, but sometimes I have the impression that they might check the data with a particular kind of spectra. Maybe if you check with different kind of astronomical object, it works in a different way. So then I'm not sure, do they provide the uncertainties? Because I have this doubt. If the data you get from VALD, do you get uncertainties from the data? So that is the big advantage I see in NIST. that it needs to have evaluated data, so you have an uncertainty to put. And the thing of the uncertainty is now, even for people producing theoretical data, there's a movement within our field in atomic spectroscopy, theoretical and experimental, that all data should have uncertainties.
Any other questions? Oh, okay.
Just out of curiosity, how does NIST or other of these databases handle molecular lines, and how they kind of vet those and distribute them to the public?
Sorry, how do they
treat molecular lines versus atomic lines?
Okay, so I don't think NIST works with molecular lines, as far as I know. There's a lot of work already with atoms. Really, NIST now is 2 people. One in the lab, one doing the compilations. It's not sustainable. The person who is doing the compilation is already saying this can't continue working. So now it's this idea that they would train all of us so that we do the compilations ourselves or something like this. In terms of molecular, I think you have other databases like Hytran, they are more focused in molecules. But I don't think it needs to have any data.
I'm just curious, what are the things you are working on right now to make the atomic parameter more precise, like say now compared to 10 years ago? And what are the things you are doing to make it more accurate?
Okay, so that's a good question. Lots of things. Maybe we have the same instruments as 20 years ago. So when the Fourier transform spectrometer appeared, the accuracy improves a lot because the resolving power is much higher. So in terms of wavelengths and energy levels, that's an increase in the order of magnitude in accuracy. With other elements, to be honest, we have better detectors now. So for example, how to measure the intensity of the spectral lines. Now with CCD cameras, the detection is much better than how it was done. I mean, still, if you want to measure at least in the vacuum ultraviolet, you use photographic plates. Of course, the intensity that we get for the photographic plates is not going to be as accurate as on a CCD camera. But on many occasions, the instruments were there 20 years ago. It's just that there's so much work to do that we just keep doing and doing and doing. So, yeah.
Let's thank our speaker again.